Hi, I'm going to present the work entitled Accuracy Analysis of Multibody System with Joint Clearances in a 4-bar mechanism. The multibody systems are kinematic chains of rigid or flexible links connected by joints. As an example, the multibody system, the parallel mechanisms have widely been studied in recent years. Therefore, it's necessary the accuracy analysis of parallel mechanisms in order to improve their performance. In this paper, an analytical formulation is proposed to obtain the structure displacement due to the joint clearances. The compliant displacement of the structure is obtained by the matrix structural analysis, and also the uncertainties that affect the performance of the mechanism were analyzed by using the Monte Carlo simulation. And in this contribution, the results of the numerical simulation are computed for a specific symmetric 4-bar linkage as illustrative example to show the feasibility and the applicability of the proposed approach. Here is present the outline of the presentation. First, the analysis of the influence of the joint clearances and the compliant displacement are applied to a 4-bar linkage mechanism that is present in this figure. These equations present the inertia, forces, and the torques that are defined as a function of the acceleration and mass of the links in the mass center of the links. Then in this figure is present the free body diagram. Therefore, the kinestatic equations can be obtained as present in these equations. These equations present an extensive model of the kinetic equations that are obtained by writing the equilibrium equations. Therefore, these equations can be written in a matrix form where Fd is the column that contains the inertia forces, L is the matrix that contains the geometrical and inertial parameters, and Fb is the column vector that contains the reaction forces that we have to find the value of these forces. Then in this matrix, we have the stiffness matrix of the joints. This matrix is function of the translational stiffness and the rotational stiffness of the joints in the principal axis. Then is defined the stiffness matrix of the three-dimensional bar, which correspond to the links that is present in this expression. And finally, the stiffness matrix of the joints and the links are expressed in a common reference frame with the height of the TJ matrix that is defined based on the kinematic model of the mechanism. And after the application of the boundary conditions, the displacement are known by using the expression shown in equation 8. The displacements are function of this invertible stiffness matrix, and also the vector W, which corresponds to the forces applied to the mechanism. Finally, we have the joint clearances model. Each clearance introduces 2 additional degrees of freedom in the mechanism. We have a displacement in X and Y, the Y-axis. And finally, we have the Monte Carlo simulation. This is a numerical method that allows computing the numerical response of the mechanism. Then we have the vector that join the uncertain parameters, which are the stiffness of the joints and the clearances, and an external force Fy that is applied to the mechanism. Each uncertain parameter is modeled as a random variable by using the expression of equation 10. And the Monte Carlo simulation has 3 main stages. First, the uncertain inputs are sampled. Then the response of the mechanism is computed for each uncertain input. And finally, a statistical analysis is applied to compute the uncertain response. In this diagram, we observe the numerical method applied to compute the numerical response. In this section, the numerical simulation of the asymmetric 4-bar linkage was carried out. In this figure, we observe the definition of the mechanism. And it's important to define the point P, because we are going to compute the response in this point, in the point P. Initially, the uncertain parameters, the geometric parameters of the links are defined, the Young modulus of the links, and also the uncertain parameters, which are the external force, the stiffness coefficients of the joints, and also the additional degrees of freedom of the joint clearances. In this way, 100 samples were considered in the Monte Carlo simulation. The kinematic model in the points A, B, P, D, and E were also formulated, and the simulation consists in computing the flexible displacement of the point P by using the matrix structural analysis and the uncertainties with the Monte Carlo simulation method. In this table, we present the structural response of the point P for different theta angles from 0 to 360 degrees. And in this way, we estimate the mean and the standard deviation for the X and Y coordinates. And we observe, based on the results, that the standard deviation increases when the conditional number of the mechanism also increases. Therefore, in the singular positions, the uncertainties have a great effect in the displacements of the point P. Then we map the stiffness. This figure presents the stiffness map. In these results, we do not consider the singular positions. And first, in this figure, we present the maximum and minimum limits of the envelope. and the reference corresponds to the response of the point P with the nominal parameters. Then in the second figure, we observe the samples considering the simulation. And we observe in this stiffness mapping the effects of the uncertainties, of the uncertain parameters in the response of the mechanism. Finally, we analyze the response when theta is equal to 30 degrees. And in this way, we plot the histogram for the X and the Y coordinate, and we estimate the density for both displacements. And we observe that a normal density approaches the behavior of the histogram. As a conclusion, this numerical approach present in this work permitted to estimate the structure response by considering the uncertainties on the clearances and also in the joint stiffness. The compliant displacements in the presence of the uncertainties affecting the clearances, input loads, and stiffness of the joints were when computed by using the Monte Carlo simulation. The numerical results allow to evaluate the effect of the uncertainties in the mechanism, and future work will consider the experimental response of the mechanism in order to evaluate the numerical approach present in this contribution. Finally, thanks for your attention.